Welcome to Calculus 1. At Grand Rapids Community College, this is a MA 133 course. The textbook we are using is Calculus 8th edition, Single Variable Calculus, Early Transcendentals by James Stewart. Here's a bigger picture of it if it helps. Because this is an online course this semester, due to COVID, we are going to be using WebAssign. Look on Blackboard and make sure that you have the information you need in order to access and hand in your homework assignments. The first thing we're going to cover is Chapter 2. It's about limits and derivatives. This first unit will consist of sections 2.1, 2.2, 2.3, 2.5, 2.6, 2.7, and 2.8. Again, this is for the particular textbook of the 8th edition of Stewart Calculus. We're going to start off first with the tangent and velocity problems. This first section may seem a little intense, but believe it or not, you're really just looking at the slope. In order to make the arithmetic easier, make sure that you have a graphing calculator. We're going to use that thing a ton. So as we get started here with the tangent and velocity problems, here's going to be our focus. We're going to look at how the idea of secants play a key role in solving tangent and velocity problems. The first tangent problem that we are going to look at is the graph of x cubed minus x plus 2 looks like this. And the point 1, 2 is just beyond the minimum. And what we want to do is figure out what the equation of the tangent line. Now, what is a tangent line? Well, let me use an example. If I have a circle and I were to draw a line through it, that line goes through the circle at 2 points. That is not a tangent. That is called a secant. A tangent, if you also consider a circle, imagine that you had a circle and you were going to line it up against a wall. That wall would touch the circle in one place. And that would be considered a tangent. Now, mind you, it's not that a tangent can't touch twice. It can for different shapes. But if I'm looking for a tangent of a line at a specific point, imagine I have a straight edge. That's going to be the line that goes through this point on the curve and shows me the direction in which the curve is moving at that particular time. So let's look at another graph of this function. We want to observe that a tangent can intersect the graph at more than one point. It always just depends on what the curve looks like and where the tangent line is. All right, so now what we're going to do is we are going to look at this function. Here I have a graph of this function on the coordinate plane, and I'm going to show you what it looks like when we're trying to find the tangent. First thing we're going to do is we're going to consider the point a equals 1. But as you can see here, I really could pick any point that I wanted to, right? I could pick any point that I wanted to in order to make a tangent at that point. Now what I'm going to do is I'm going to show you what the tangent line would look like at that point, regardless of what tangent line I have. Okay, what I'm going to show you now is what the tangent line would look like at any point on this graph. Okay, so what I'm going to do is I'm going to drag this point. So here's my function, x cubed minus x plus 2. And here are all the tangent lines at all the different points on this graph. Okay. Now, if I wanted to find the tangent line at x equals 0, that would be the tangent line at x equals 0. Okay, if I wanted to find the tangent line here at about the maximum, notice that the tangent line, let me get right on top of the maximum, it's so hard to get close. Okay. Notice, even though the tangent line touches this graph at another point, it's still the tangent line to that point there on the maximum. Right? So, the tangent line can touch the graph more than once, but what we're looking for is the line of the tangent at a particular point. And in this case, we are looking for the equation of the tangent line at the point 1, 2. So we're trying to find this equation right here. Okay, by the way, I'm kind of new at this whole recording thing, so we will see how this goes. We revamped the Lightboard a couple of different times for GRCC in order to help all the teachers use it, and I'm still learning. So if you see me bopping in and out of focus, or you notice me struggling with the technology, I apologize. We're all learning stuff, the new stuff these days. Okay, so what I wanted to do was also show you a secant for this function. So notice this, I have 2 points here. I've got the point where I'm trying to find the tangent, and I'm trying to find this tangent equation. And then I've got another point over here. Now this pink line creates a secant. This yellowish greenish line is the tangent. Notice, where do I have to move this other point in order to get the secant to behave like the tangent? So just think about this. Where do I need to move this pink point? Along the graph of x cubed minus x plus 2. Where do I need to move this second point to get the pink line to behave like the yellow-green line? Yeah, that's right. I need that pink point to be very, 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 very close to the point at which I'm taking my tangent. In fact, if I were to zoom in on this, they need to be super-duper close, right? They need to be really close. Okay. So graphically, this is what we're going to do in this example. Note, it's fairly tedious, okay? In order to find the tangent, we're going to learn a faster way to do it. But in the beginning here, what we're doing is we're finding theoretical tangents. We're finding tangents that use limits to prove their existence. And so what we're going to do is we're going to take a secant, which remember is 2 points. And we're going to take those 2 points and we're going to move them closer and closer and closer together so that we can find where the secant behaves like the tangent. Okay? And a secant with 2 points really, really close together does behave like the tangent. All right, so let's get back to the problem. Let's put away this graph for a second. Okay. So we've already looked at a graph of the equation, and we've taken a peek at what the tangent line might look like. But now what we have to do is find that mathematically. So just remember, we're going to find the equation of the tangent line. Well, how do we find the equation of a line? First of all, we use the point-slope formula. This guy right here. Not here. It's over here. We're going to use the point-slope formula. Y minus y1 equals m times x minus x1. This is very well named. It's called the point-slope form, okay? It's called point-slope because you need a point and you need a slope to plug into it. All right, so we're going to take 1 point. We call that x sub 1, y sub 1, and that's going to go here into our equation. And then we're going to find the slope. Now, remember, in order to find the slope of the tangent line, we do need 2 points. So this is where we're going to use those secants in order to find the slope of the tangent line. Okay, you ready to find the equation? Me too. Remember, whenever you find the equation of a line, first you have to find the slope. So that's where we start our subproblem. Okay, so remember, 2 points. What we're going to do is we've got 2 points here. We've got this point, the original point, 1, 2. That point we know. So we can get on top of it here. This guy. Okay, this is point P. This is my original point, 1, 2. And then I have some arbitrary point on the curve. And I'm going to call that point Q. Okay, so we're going to imagine that there is a point Q that is getting closer and closer and closer to point P. But in order to do this, we can't just pick a value. What we need to do is assign it some arbitrary values. So first of all, we're just going to imagine that point Q has some x value x. We don't know what it is. Next, what we're going to do is we're going to say, okay, if it's point x, then the y coordinate for this line is given by the curve, the x cubed minus x plus 2. So these are going to be my 2 points that I'm going to use. Now, how do I find the slope of 2 points? Okay, so again, remember, we have 2 points. The original point P, which is where we're trying to find the slope of the tangent line at point P, and then some arbitrary point Q. And the idea is that we want to imagine that point Q is getting closer and closer and closer to point P. So if I'm trying to find the slope of these lines, of this line, keep in mind that this is the slope of the secant. What I'm going to do, remember, is I'm going to take the y coordinate of one, subtract it from the y coordinate of the other. And then I'm going to divide that by the x coordinate of one and subtract it from the x coordinate of the other. I want you to be mindful whenever we do this, it's good to always do the arbitrary point first. We always want to do arbitrary minus specific. Okay? So keep in mind, you want to do arbitrary, which is the Q point. You can't see that. Sorry, arbitrary. Someone wrote a little thing here and that doesn't work. Okay, so you want to have the arbitrary minus the specific. Okay, so the arbitrary is point Q. The specific is point P. So if I'm going to find the slope of the secant for this bad boy, what's the y coordinate for point Q? And then I will subtract from that the y coordinate of point P. And then I divide that by the x coordinate of point Q and the x coordinate of point P. So I'm going to switch colors because the squeaking is kind of driving me bonkers. Let's go ahead and take a look at this. So what's the y coordinate of Q? Yeah, here's the y coordinate of Q. So this one's going to be x cubed minus x plus 2. Now I need to subtract the y coordinate of P. Well, here's P. The y coordinate of P is 2, so I'm going to subtract 2. See why we want to have arbitrary minus specific? When I subtract a number, that's not that big of a deal. Subtracting an equation can be a big deal and can cause issues if you forget to distribute your sign. So always do arbitrary minus specific. Let's continue the same thing for x. So I want to find the x coordinate of Q. So here's Q. My x coordinate is x. And then I want to subtract from it the x coordinate of P, and that is 1. So the formula for the slope of my secant is going to be x cubed minus x plus 2 minus 2 over x minus 1. Now, you don't have to simplify if you don't want to. You can just use this because we're going to be looking at the numbers behind this. But notice that that plus 2 and minus 2 cancel each other out. So at the top, I would just be left with x cubed minus x all over x minus 1. Again, we're going to be doing the math with this, but it will simplify a little bit more. But keep in mind that either this right here you could plug into your calculator, or this right here you could plug into your calculator. As we get going in this class, we'll learn how to do more simplifying, and we'll talk about how to find the slope of the tangent. But I digress. Let's continue with this long problem. Now it's time to look at the work. Keep in mind what we're going to do now is we're going to create a table of values. Understand that the table of values is based off of Q as Q changes. So here's our original point, and if we put point Q on top of point P, understand that that means that the x-coordinate of Q is 1. And if we found the slope of the secant when the x-coordinate is 1, we would get 1 minus 1 on the bottom, right? And if we did that, we would get the slope would be undefined, right? Not 0, but undefined. We can't divide by 0. That's a no-no. Keep in mind, too, that if that point Q was right on top of point P, the y-coordinate would be 2. Okay, so you can use your calculators to fill this out. What I'm going to do is I'm going to use my calculator, and I'm going to put in for y1, I'm going to put my original equation. X cubed minus x plus 2. For my y2, I'm going to put the equation for the slope of my secant. Okay? All right, so notice here I've got points that are very far away from point P. Here I've got x equals 3, x equals 2. And then as I get closer to it, I'm picking values of Q that are very, very close to point P. Very, 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 very close to x equals 1. So what I'm going to do is I'm going to work backwards. All right, so if I plug 3 into the original equation, if I plug 3 into this x cubed equation, I'm going to get 26. If I plug that 3 into my slope of the secant, I'm going to find that the slope of that secant is 12. Now again, keep in mind, we're basically looking at this secant line here, not the tangent line. Sorry, it's a bad drawing. Okay, next let's look at when x-coordinate is 2. If we plug that into our original function, we end up with a y-coordinate of 8. So here, I'm using this graph here is 2. It's kind of off my screen here. Y is 8. And then if I find the slope of the secant connecting those 2 points, I get 6. All right, notice that my slope is changing as I get closer to point P. All right, so now I'm going to use these other values. So I'm going to plug in 1.1, and I'm looking at my notes here, and I have 2.231. Then I'm going to find the slope between those two values, and I get 2.31. Next, I plug in 1.01 for my x-coordinate. And in my original function, the y value is 2.0203. So 2.0203. And when I look at the slope between those two, I get 2.0301. Next, I've got 1.001. Notice 1.001 is really close to 1. Got a little dot there. Okay, so this 1.001, when I plug it in, I'm going to end up with a y-coordinate of 2.002. And then the slope of the secant between those 2 points is going to be 2.003. Next point, 1.0001, okay, 1.0001, that is very close to the point of 1, and there I'm going to get 2.0002, and when I find the slope between those 2 points, I'm going to get 2.0003. Now notice, as I move in this direction, okay, as I move in this direction, my x values are getting closer to the original x value of 1. And what's happening to my slope values? Yeah. And that's my next question. So here's my conclusion. The secant, as x approaches 1, has a slope of what? As q approaches p, which is really where the x-coordinate of q is approaching 1, because the x-coordinate of p is 1, that means that the slope of my secant is equal to 2. At least it's getting close to 2. Okay, so in conclusion, what we did was we took point Q and we smushed it so that it was arbitrarily close to P. And what we did was we turned that secant into a tangent. And then what we found is that as Q got closer and closer and closer to P, the slope of the secant became closer to the slope of the tangent. And I believe as we get closer and closer and closer that 2.00000 is going to continue. And then we got the slope of the tangent, which is 2. Now keep in mind, when we move Q closer, basically what we keep doing is we keep adding zeros. Okay? So, for example, if I want to move it, if my original x-coordinate is 1, then what I'm going to do is I'm going to move it as close as possible. So like 1.1, 1.01, 1.001, 1.0001, 1.00001. And if I wanted to get real tricky, honestly, just to check my answer, I could say that 1 would be equal to 1.00000. Just really go ape crap on the zeros and then hit 0, 1. And then you'll be able to approximate that slope of the tangent using the secant. Okay, wonderful. Now we're going to look at a different type of problem. Very similar. Again, we're using the slope of the secant in order to find the slope of the tangent. Okay, and then to finish our problem, we've got y minus y1. Our y-coordinate was 2. Our slope happened to be 2 as well. That doesn't happen all the time. That's just a coincidence. And then our x-coordinate was 1. Then what I'm going to do is I'm going to distribute the 2, and then I am going to add 2 to both sides, and I get y equals 2x. And that is the equation of my tangent line. Okay? All right. So you got to find the slope of the tangent. Then you take that slope of the tangent, you plug it into the point slope formula with the coordinates of the point, P, that you're trying to find the tangent line of, and then you plug it in, and then we end up finding the equation of the tangent line. Remember, you can always check it, okay? You can always graph both your original line and your tangent line that you found, and they should graph like that. You should see your original point, your original graph, and your tangent line touching at the point that you were trying to find the tangent line. It's a good way to check it. Now we're going to look at the velocity problem. We're going to start off by looking at both average velocity and instantaneous velocity. Think of the average velocity as the secant, and think of the instantaneous velocity as the tangent, okay? Average is the secant, instantaneous is the tangent. Let's fill in the blanks. Okay, the average velocity is the velocity of an object over a period of time. So over 2 seconds, over half a second, over 15 seconds, over 2 hours. The formula for average velocity is always going to be this. It's going to be the change in position over the change in time, or delta S over delta T. Delta stands for change. In instantaneous velocity, much like our tangent problems earlier, velocity of an object at a given point in time. Okay, so it's an instantaneous velocity is not velocity over a period of time, but it's at a given point in time. So at an exact moment, how fast were they going at time equals 3 seconds after they started moving? Okay, so we're going to look at the velocity of an object at a given point in time, and then in order to find this instantaneous velocity, we're going to use limits. Okay, we actually did that before. We'll talk more about it in a bit. Instantaneous velocity is the limit of average velocities over shorter time periods. Okay, so we're going to, again, take the 2 points and put them really, really close and try to get that secant to behave like a tangent. Okay, so I'm on the planet Mars and I'm throwing rocks around. I'm going to take a rock, I'm going to throw it upward on the planet Mars with a velocity of 10 meters per second. Its height in meters, t seconds later, is given by this function. H of t equals 10t minus 1.86 t squared. The first thing I want to do is I want to figure out, okay, what's the height of this rock at any time t after I've thrown it? Now notice, this height here, this function here, is a parabola. Okay, so it's kind of a parabola that looks like this. So I want to know at time equals, 0 seconds, how high is the rock? At time equals 1 second, how high is the rock? At time equals 2 seconds, how high is the rock? At time equals 3, how high is the rock? Well, what I need to do is take this function and plug in the values of t equals 0, t equals 1, t equals 2, and t equals 3. You can use your graphing calculator or you can just do it the long way. Either way, make sure you've got correct values. Okay, now that I have these, I can look at what's the average velocity of this object between t equals 0 and t equals 1. So what I'm really going to do, in order to find the average velocity, remember, you can't see that. In order to find the average velocity, you're going to find the slope of these values. So, okay, so we are going to look at from t equals 1 to t equals 0. So t equals 1 is this value right here. Which one's the t value? Which one's the output value? Yeah, my output value is 8.14. Okay? And I'm going to subtract from that my t equals 0, my output value there. Okay? So in other words, I'm taking the slope, remember? So I'm like taking y sub 2 minus y sub 1. That's what's happening over there. Okay, and over here, I'm going to do my x sub 2 minus x sub 1. And I'm going to go from t equals 1 to t equals 0. So I'm going to take 1 minus 0. So x value of 1 minus x value of 0. And this average velocity that I've got here is 8.14 divided by 1, which is simply 8.14. And the unit is in meters per second. All right, now for the next problem, we're going to find an average velocity between two different values. So now I'm going to find the average velocity of the object between t equals 1 and t equals 2. All right, so t equals 2 is this set of values. T equals 1 is this set of values. So for t equals 2, I'm going to take the output value first. That's 12.56. And I'm going to subtract from it the output value of t equals 1. And then I'm going to take the x-coordinate of t equals 2 and subtract it from the x-coordinate of t equals 1. Sorry, I guess it's a t-coordinate. Okay, in other words, though, remember, I'm finding my delta s over my delta t, or my output difference over my input difference. So if I subtract that, I end up with what? 4.42 meters per second. And that's my average velocity from time equals 1 to time equals 2. But what if I need to find an instantaneous velocity? Yeah. If I need to find an instantaneous velocity, I have to figure out where am I going to find the instantaneous velocity. Am I going to find it at t equals 1? Am I going to find it at t equals 2? Am I going to find it at t equals 3? Where am I going to find it? So now we're going to find an approximate value of the instantaneous velocity when t equals 1. Okay? So 1 second after I have thrown the rock on Mars, what's the instantaneous velocity of that rock at that moment in time? So just kind of imagine, get my bearings here. Here you are throwing a rock on Mars, okay? And at t equals 1, what is the velocity of that rock? It's kind of like taking a picture at that moment and freezing it in time and then looking to see how fast is it going. Well, keep in mind, our t value in question is 1. Okay, so we have to look at different values close to 1. What values would you use close to 1? Good. Those are the values I use too. Okay. I already know that if I want to get really close to 1, I'm basically going to keep adding 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1. I'm going to keep adding zeros. And then I'm going to plug those values into my original function. Okay? So keep in mind, in order to find this h of t value, that's my original function. That's not the slope of the secant. Okay? Next, if I want to find the slope of the secant or the average velocity, then I can find the slope of the secant and fill out the next table. Okay, so my first interval I've got from time 1 to time equals 2. I'm going to find that average velocity, which I actually found that in the previous problem. That's my 4.42 meters per second. Okay. Now next, if I want to find these other, I'm going to work through one of them and then I want you to do the others. So remember, this is the slope of the secant. And what I'm going to do is I'm going to take the change in position, which in this case is height, so it's the change in height, and I'm going to calculate that over the change in time. Okay? So from 1.1 to 1, I'm going to start with 1.1. 1.1, I have a y-coordinate of 8.7494. I'm going to subtract from that the height at 1, which is 8.14. And then I'm going to calculate the difference between the t values. T value of 1.1, I'm going to subtract from that the t value of 1. And in this case, sorry you can't see this, this is 8.14. I went off the edge of my board here. When I find this slope of the secant, this is going to give me my average velocity. And in this case, I get 6.094 meters per second. Okay, now I want you to do the exact same thing. Fill in these things. Fill in these boxes using what you have here. Keep in mind, if you'd like to use your calculator, you totally can. Save yourself some time and maybe some hassle. If you're going to do the slope of the secant, remember, you always do arbitrary minus specific. Okay? So you would take the equation first, which is the 10t minus 1.86t squared, and then you subtract from it the y coordinate. Okay, so this is basically the arbitrary minus specific. I'm sorry, you can't see that. Let me write it up here. Okay, slope of the secant equals 10t minus 1.86 t squared. Shaking it by pushing on it so hard. And I'm going to subtract from that 8.14. Oh, good. The markers are protesting. And then in the denominator, I'm going to put the difference of my x values or my t values. So I'm going to have t minus 1. So remember, I always take the arbitrary minus the specific or the equation minus value. I just wrote again. You couldn't see it. Equation minus value. Sorry, still learning. Okie dokie. Go ahead and pause this video and then create these values. On your mark, get set, pause. Did you get these values? Good. Now, keep in mind, what point values are you getting closer to the instantaneous velocity at t equals 1? Which one's the closest interval? Yeah, it's that bad boy on the bottom right there, okay? From t equals 1 to t equals 1 point, what is that, 00001? 00001? That is extremely close. And so this value right here, we can say, okay, at this point right here, the instantaneous velocity is pretty close to the average velocity. We're not going to say that they're exactly equal to each other, but they are approximately equal to each other. And that's totally true. So in conclusion, we can observe that as time intervals get smaller and smaller and smaller, the average velocities approach 6.28 meters per second. Therefore, we conclude that the instantaneous velocity of the rock when t equals 1 second is 6.28 meters per second. Now you know what to do if you're throwing rocks on Mars, right? All right, what you can't see is that erasing this light board is a huge pain in the butt. But if we were in person, I would be teaching you this on the board, and you could ask me questions. But that's not the case. This is all going to be online because stuff got a little cuckoo for Cocoa Puffs recently, didn't they? So make sure to get online when you can in order to ask me questions. Otherwise, calculus is going to be just as difficult as all this COVID crap we're going through right now, right? Wash your hands. I'll see you in a Zoom meeting soon. Work on your homework. If you have any questions, make sure to contact me, okay? Bye. All right, what you can't see is that erasing this light board is a huge pain in the butt. But if we were in person, I would be teaching you this on the board, and you could ask me questions. But that's not the case. This is all going to be online because stuff got a little cuckoo for Cocoa Puffs recently, didn't they? So make sure to get online when you can in order to ask me questions. Otherwise, calculus is going to be just as difficult as all this COVID crap we're going through right now, right? Wash your hands. I'll see you in a Zoom meeting soon. Work on your homework. If you have any questions, make sure to contact me, okay? Bye. I don't know why I blew a kiss. This is just very strange to do it this way. There's no one here. No one can laugh at my jokes. I always think always think I'm funny, but sometimes I know I'm not.